Hello and welcome to the Digital Culture Speaker Series. Today with us, we have Frank Liu. Frank's a fourth-year computer engineering PhD student who studies under me, Robert LiKamWa. His research is at the intersection of mixed reality, haptics, and education, where he works towards building a metaverse you can feel, which is what he's going to be presenting on today. His works have been published in top human-computer interactions conferences such as UIST and IMWUT. He has also had works published in AIVR, ILRN, and MobileHCI. At ASU, Frank's been the recipient of the prestigious Dean's Fellowship and the Herbold Foundation Fellowship. Outside of research, Frank was actively involved in building up the ASU community through leadership roles in sunhacks and TedXASU. Prior to his PhD program, Frank graduated from the University of Washington with a degree in electrical engineering in 2018. He received departmental honors in electrical engineering there, but we're so lucky to have him here with us today at ASU and here to give us our talk. Thanks, Frank.
All right. Thank you. Thank you. Thanks, everyone. My name is Frank Liu, and today I'm going to be giving a talk, a metaverse you can feel, building haptics for mixed reality. So Robert already gave a little bit of introduction. I'm just going to give another introduction about myself. So I graduated with a Bachelor's of Science in Electrical Engineering from the University of Washington in 2018. And two of the most impactful experiences that I had at UW, the first one was as an undergraduate researcher working in the ubiquitous computing lab. And the second experience was my time as an electrical engineer in the advanced robotics team, or ARUW. During my time on the team, we built robots. And that's kind of where I fell in love with the integration of hardware and software. I'm currently now a fourth-year PhD student in computer engineering, and I'm advised by Professor Robert LiKamWa. I'm part of the Meteor Studio. So throughout my time at ASU, I've had the wonderful opportunity to work with many great collaborators. The first one is my professor, and also other professors such as Dr. Byron Leahy, who's AME faculty, Dr. Mina Johnson, who's psychology faculty, Shahabuddin Sageb, who's currently Virginia Tech faculty and formerly AME staff. I also have the privilege to be working with many undergraduate students across many different disciplines, such as AME, CS, ME, and chemistry. So over the past 4 years, I've been doing research in haptics that advance the way users interact with virtual objects in VR and AR. I'm studying and designing new mechanized apparatuses that connect the digital and physical world. I'm really interested in the intersection between education, mixed reality, and haptics. But why do I care about this so much? Well, there's a little thing called the metaverse. With AR and VR, people are creating virtual worlds filled with programmable virtual experiences, connecting people to socialize through virtual networks. And people have even started to consider using virtual reality for education and workforce training to be able to connect learners with these virtual experiences. There are virtual labs like Labster, and these virtual labs bring aspects like remote accessibility, safe exploration, and interactive programmability for the user. When I think back and look back on my experiences in education, I think where I learned the most was my hands-on projects, hands-on labs, so I could tangibly understand things like physics, chemistry, robotics. So it's really good that these virtual reality experiences are starting to give people those kinds of experiences, even in remote or virtual education settings. But something is missing. There's something missing from these virtual labs. And that is the sense of touch with these tangible objects in space. When playing around in VR, you often have the controllers that can sense where you're moving your hands, but they don't really give the sensation of actually touching an object in VR. They don't give the sensation of manipulating objects in these virtual settings. And at most, these virtual controllers might vibrate, usually programmed as a response when your controller interacts with a virtual object. So there's a need for tactile lab skills. With only the virtual aspect of virtual labs, with only the visual aspect of these virtual labs, this removes the virtual experiences from really representing the physical reality of virtual labs, as well as other educational virtual experiences. If we want to teach students real lab skills, if we want to train workers on handling the equipment, then we better approximate these physical sensations that they would get in these environments. We want students to be more engaged, not distracted or bored. We want to make students feel like they're really part of the environment, like they're actually interacting with objects in these environments. So that's why I'm really interested in the metaverse you can feel, especially with building haptic devices for virtual science education. So my line of work is inspired by prior work in this area, where others have produced virtually controllable haptics and created different sorts of illusions. So here are a couple of examples of haptics for grabbing. We have Wolverine and Gravity from Stanford Shape Labs, as well as Capstan Crunch from Microsoft Research. These are just 3 examples of devices that give the physical sensation of grabbing onto virtual objects. There are also other examples that use different types of dynamically changing devices for haptics in VR. To the top left, we have Thor's hammer. And Thor's hammer uses wind to generate forces when interacting with objects in VR. We have Shifty that uses a shifting weight that moves the center of mass up and down to simulate larger or smaller objects. We have Haptic Pivot that uses a pivot to pivot an active weight into and out of your hand to render different types of forces like grabbing and dropping. And we also have haptic bots. And these are just little robots that move around, that actuate different surfaces up and down that correspond to when you're touching different virtual surfaces. So there's a lot of potential for haptics in VR. And that brings us to augmented fluidity. You see, not all school districts have the means to be able to offer a science lab curriculum. Affordable, accessible, mixed reality enables students to make mistakes, to break things in VR, to iterate on their experiences in ways that traditional labs can't. So as a result, I'm really interested in creating those similar sorts of illusions to be able to produce novel physical sensations. We want to be able to provide learners with virtual apparatuses that provide the physical sensations that they would experience in a physical lab. Towards that, I'll talk about some of our works today, such as fluid vessel haptics, mixed reality titration experiment, and augmented reality experiments and assistance. I do want to mention that in all of these, we're really interested in affordable and accessible production. I don't want my devices to be just available to a few. Through 3D printing, commodity electronics, simplified assembly, I hope to democratize this sort of research. We're also really studying the impact of improving educational outcomes. What does it mean for students to use these devices, and how does that translate into tangible learning improvements? So going into our first topic of fluid vessel haptics, called swish. So one common experience from a science lab is mixing and interacting with fluids. So that brings us to a couple questions. The first one, how do we generate haptic sensations when interacting with fluids in VR? 2, how do we do this with programmable fluids of different volumes and viscosities? And 3, how do we make virtual fluids interact with each other for chemical reactions? So just kind of considering our day-to-day interaction handling of liquids and containers. What are we actually feeling? So I have my water cup here, and it's filled with liquid. And I move it around, I can kind of feel the weight of the moving liquid. But more specifically, I feel the moving of the center of mass of that liquid. And that was the insight that we decided to build upon. So, swish. This is where I introduce a shifting weight interface of simulated hydrodynamics. So essentially what we do is we take the center of mass of virtual fluid and we translate it into R, H, phi polar motor commands. You see that on the left, right here, where we have the virtual fluid, and then the red ball marks the center of gravity of that virtual fluid. Swish actuates a moving mass in a racking pinion system. So the motor commands that are generated from here are sent to this moving mass right here. So this is our racking pinion system. So I'm going to share a quick video about this work. So what we found from swish, we compared swish with we had 3 identical buckets. The first one was filled with physical liquid. The second one was our swish system. And one was a bucket with just solid weight. And from our user studies, we found that swish performed nearly as good or as good as a bucket filled with physical liquid across actions such as sway, swirl, flip, roll, jump, and saute. And we also found that swish performed much better than a static weight as well. So rack and pinion system works, right? End of story. We can call the day over. Well, not quite. You see, in real science labs, not everyone uses these large buckets to conduct experiments. Actually, it's quite rare. We actually have conical, spherical, elongated, and many more differently shaped containers to be able to interact with in real science labs. If we had a multitude of different vessel profiles, then the weight from the rack and pinion system probably wouldn't reach all areas of the shell profile. So just as a mental exercise, just try and imagine a conical flask fitting over the rack and pinion system. If you really imagine it, right, we would see that the weight probably wouldn't reach the corners on the sides. So, as a work in progress, we really had to rethink our actuation mechanisms to be able to make these different vessel profiles possible. And on the table right here, we have the example of what those devices are. You guys can check it out after the talk. So wrapping up for fluid vessel haptics, we have a vision for widespread use in high school and college science classes. We want to be able to democratize science for all, to be able to build the experiences of the future, asking ourselves, what can we do with virtual fluids in the context of VR? So next, going on to the mixed reality titration experiment. We wanted to contextualize the use of these sorts of virtual experiences into virtual chemistry labs. And we were thinking of ways of bringing common science curriculum into the 21st century. So the virtual chemistry lab was first started by an undergraduate named Charles. Charles had a dream of being a high school chemistry teacher, and he currently is one right now. When we first met, he wanted to develop a common experiment in mixed reality. So together, working with Charles, we developed a virtual titration experiment. Scientists use virtual titration to neutralize an acidic solution to determine its concentration. You would slowly add a volume of a solution of known concentration to a volume of another solution in order to determine its concentration. So with this lab, we want students to learn two things. The first is what a titration experiment is, and the second, to have students develop real lab skills.
Once in the scene, the user is able to turn the physical dial to trigger the virtual burette to release its fluid at a rate the user chooses. As base from the burette collides with the acid in the beaker, the mixed fluids change color from clear to pink, remain pink momentarily, and then return to clear. This imitates the effect produced by the phenolphthalein indicator commonly utilized in acid-base titrations. As the user continues to add base to the acid, the reversible color change in the beaker lasts longer. This is another one of the key observations students are advised to make while performing a titration. The experiment ends when the color change persists permanently, representing the endpoint. The endpoint is the point at which all of the acid in the beaker has completely reacted, leading an additional drop to cause an irreversible color change.
So we also designed and built 3D printed burettes so that students can develop this tactile lab experience, as if they're turning a burette in the classroom. We have version 1 on the left, and we also have version 2 on the right. These are very simple and easy to build. They're made up of an Arduino, a potentiometer, breadboard, a couple wires, and a resistor. We're also studying how haptics improves learning, working with Professor Johnson to be able to study the impact of our haptic device. So far, we developed a full lab experience with pre-test and post-test questions. And we're currently working with Mina's students, Alice Bao and Christine Yu, to be able to measure the effect of the haptic experience. And so far, we have many students who have gone through these early college who have taken intro chemistry and kind of seeing how this experiment really improves or impacts their learning. So lastly, I'm going to be talking about augmented reality experiments and assistance. And so these are just a couple of projects where I've mentored undergrads to lead these projects. Ryan Rajati led the specific heat experiment, and Mason Ulrich led the air-sun chemistry models. So a specific heat experiment is commonly performed in middle school and high school labs. Students can measure the temperature of a liquid over time and see what it takes to maintain the heat of that liquid. By making this experiment virtual, educators can use this as a study tool and have students measure the specific heat of liquids that they might not otherwise have access to.
Once in the app, the user first has to scan a predetermined image target to display the augmented chemistry lab. The user then has the ability to dispense a given amount of water into the virtual beaker and begin the experiment. The experiment, however, will only begin once a bunch of burners is on and the simulation is running. Students should then record the temperature of water in equal intervals, which can be made easier with the play pause functionality. While in the app, the user should also record the heat output in joules per second, the mass of water, and the time it took for the water to boil. All of these values will later be used to calculate the specific heat of water. In our experiment, once the water reaches 100 degrees Celsius, it will begin to steam, emulating the boiling of water. Students will then know that the experiment has ended, and they should continue by plotting the recorded temperature points. They should get a positive linear slope that plateaus once the temperature reaches around 100 degrees Celsius. To calculate the specific heat of water, we use the heat capacity equation C is equal to Q divided by M times delta T. Using the constant 1000 joules per second multiplied by the total time of 210 seconds to reach boiling point, it will equal 210,000 joules, which gives us our Q value. We then divide Q by the mass of 500 grams times delta T, which is 100.33 degrees Celsius, which gives us a final value of 4.2 joules per grams times degrees Celsius. This value is similar to the actual heat capacity of water, which is 4.18 joules per grams times degrees Celsius.
Also, for younger students who like to kind of mess around, they don't have to worry about the students burning themselves on the Bunsen burners. And so this also is kind of a simple, easy way for students to get introduced into science experiments. And lastly, we developed AR Sum chemistry models as a chemistry study tool. Many students, including myself, have had trouble identifying molecules. It would have been really great to be able to draw the molecules down and then see it in real time. Currently, students use ball and stick models where they fit the balls and sticks together, Lego style. But these are kind of hard to build and time consuming when you have more complex molecules.
In organic chemistry, students might encounter a complex molecule they are unfamiliar with or are struggling to understand. Our application uses augmented reality to increase the number of studying methods available to students by turning 2D line angle structures into 3D models that can be manipulated and inspected. This makes lecture presentations more interactive, gap notes more informative, and studying more effective. Students primarily learn chemistry through drawing molecules and recognizing functional groups. We designed our app to enhance this form of practice by allowing the student to draw out molecules and visualize their 2D drawing in 3D. If a molecule does not appear when the student scans it, they know that they made a mistake and must reattempt drawing the correct 2D structure. When a student presses on the functional group present in the molecule, it is highlighted and gives more information about its purpose. This helps to build context around these complex chemistry topics and relate them to information that the student may already know about.
So let's go back to our in-person labs again. And I'd like to ask you guys a question. What makes these in-person labs engaging? Or what do you think might make them more engaging? Question to the audience. Alex.
You have like a, you might be with a group and you have these like physical things that you can feel and play around with. Sort of there's a lot of factors that go into it.
Okay, sure. Any others?
Having two little boys, I know that being able to hurt yourself and catch things on fire is a feature, not a bug.
Being able to laugh and play together, I think, a little bit and make fun of each other while you're messing up too, and burning yourselves probably is also another aspect.
Lab outfit.
Yeah, great answers. So when I'm thinking about my experience in chemistry, biology, or physics lab experiments, some things that I really enjoyed was having that hands-on experience and even seeing and mixing those fluids in front of me. But I think reflecting, I think the most helpful was working with other people, having that opportunity to be able to work with other people, and really going through the science experience together and talking with the results. I remember my freshman year of chemistry, I didn't really know very much, and my lab partner knew a lot. And so it was really great to be able to talk to my lab partner and go through it. Thank goodness to my lab partner, and I passed that class. But ultimately, what I'm trying to say is it's really working with people that makes these in-person labs meaningful, I feel. So for the future of what I'm looking towards is to be able to develop network haptics, where users can be able to feel the metaverse together. And so some questions I'd like us to think about is, what does it mean for users to be able to feel the same metaverse together? What form factors will emerge? How many gloves are too much? And where are the intersections of technology that can make this a reality? And we started to see some works from Haptic gloves on the left, as well as Meta Reality Labs in working towards this future. So exploring this, I'm exploring this with a project that I'm currently working on, and it recently got accepted to a CHI workshop, Sustainable Haptic Design. as well as an upcoming partnership between Meteor Studio, Komatsu, and Haptics. So Haptics, like I've shown in the last slide, develops really high fidelity haptic experiences for gloves. Komatsu develops mining equipment and construction equipment. So we're really partnering with them to kind of understand what is the future of training in workplace environments. How do we be able to create these experiences that can help and have people learn? So in summary, with novel physical sensations and augmented fluidity, we want to be able to provide learners with virtual apparatuses that provide the physical sensations that they can experience in a physical lab. I went over 4 different aspects of work that I'm currently working on: fluid vessel haptics, mixed reality titration experiment, augmented reality experiment and assistance, as well as network haptics. So tying everything all together, my work has 3 themes. The first one is being able to have programmable, novel physical sensations, to be able to develop devices that can create these sensations that you experience in a science lab. The second theme is accessible and affordable production. As you've seen from the virtual haptic burette and also our swish device, we want to be able to have these devices easily created through 3D printing, electronics, simplified assembly. And last thing is we want to improve educational outcomes, to be able to see the impact of how our haptic devices can improve student engagement, student learning outcomes. So that wraps up my talk. Thank you all.
All right, do we have any questions for Frank? How long does it take to print, I guess, pick any of one of your apparatuses?
I think if we're really putting our time into it, it takes about a week to 3D print everything all together. But we are kind of working on finding ways to make the design simpler and more easy to build. But this is just kind of our starting point.
Interesting. Other questions from the audience? Is there anything on Zoom?
Are you doing like tests for
Yeah, so if
his question or the
what?
Repeat his question so Zoom can hear you.
Okay. So the question is, are we doing tests to see whether these haptic devices improve the virtual learning experience? And the answer is yes. I'll go back to the haptic devices for the haptic burette. We're developing the different chemistry experiments, and also if you see over there, we've created a new device for the fluid vessel haptics, and kind of our next steps are to kind of explore this integrated into different science curriculums using VR.
Are you seeing any, I guess my question more was like, what are you seeing any data come out, like is the data interesting so far?
Yeah, so we currently have maybe, I think Christine said we had about 130 students go through it so far. And we also collect videos from the students after the post-test, and the students who go through the burette kind of have, when they're explaining the learning experience, they have more gestures kind of towards that aspect. But we're still working on processing that data.
Are you testing VR versus screen-based with no VR, or are you testing like the VR versus in a lab with physical equipment?
Yeah, so for this specific one, we're testing the haptic burette by itself with just the arrow keys of moving the burette. And just this is kind of our starting point. And once we kind of understand that, just the specific impact of the gesture, we're looking to expand to making it in mixed reality and getting that all together.
But everything would be the same, right? You do the same app,
Right.
But it would be, instead of the haptics, you just use the arrow.
Right.
Everything is the same except for the one input mechanism.
Frank, I have a question. This is Byron.
Hello, Byron.
How you doing? So this is a really great talk, and I'm interested in the final topic, the theme of networked haptics. I think that's a really interesting component to really be starting to think about and bring in. Most of what you've presented, and actually most of what is in the field of haptics, centers around the hands, and for good reason, because we interact with the world largely through our hands. But it seems really evident that there's a whole rest of the body that is potentially engaged. And that may be especially true if you start thinking about a more networked sort of social thing where, you know, a hand on the shoulder or something might be really significant. And how would you feel that? So have you thought of anything about anything beyond sort of what we do, what we hold or touch with our hands?
Yeah, that's a really great question. I think current works is just being able to start off, how do we grab and throw objects together to each other? And then kind of once we establish that baseline of being able to just interact with them together, we can kind of build on that into more different sorts of form factors that people can wear, or adjust our existing devices to other parts of the body that can create those sorts of sensations.
That's great. Thanks.
All right. Well, let's thank Frank. And we'll see you all next week. Thanks for coming.